Welcome to Massive Open Online course on Fluidization Engineering. Today's lecture will be on bubbling fluidization part 2. Here also the bubble characteristics in the bubbling fluidized bed will be discussed. In this lecture, we will see how that bubble is growth and also how bubbles are splitting into parts and what will be the required mechanism for that in the bubbling fluidized bed. We will be trying to learn something about this. Now, in this case you will see that the bubbles in fluidized beds that grow in size due to primarily to actually some several factors, mainly 3 factors we can observe in the happening of that growth of bubbles in the fluidized bed. First is the effective hydrostatic pressure, which may affect on the growth of the bubble from the distributor in the fluidized bed. In that case, the effective hydrostatic pressure decreases the bubble size toward the top of the fluidized bed, and bubble coalescence in the vertical direction with the trailing bubble that catching up in the leading bubble, and this mechanism because of certain that is distance to arrive to this leading bubble, then there will be catching of that bubble, and then coalescence of these 2 bubbles will happen. Now, in the horizontal direction you will see that bubble coalescence will be based on the neighboring bubbles, and there of course, the side by side collisions of the bubbles in the horizontal cases. So, there also the bubble growth will be just colliding of 2 bubbles maybe the horizontally by colliding to each other side by side, whereas in the vertical cases of course, one bubbles will be going upward followed by another one, and then the tailing bubbles of course, will catch up that the tailing that another bubbles vertically and making a bigger one. So, that the bubble size will be increased from its initial diameter or size. The effect of the hydrostatic pressure is usually small in this case, and you will see that higher pressure sometimes will reduce the size of the bubbles, and then coalescence may hindered because of some other fluid properties. And also at low pressures you will see that there will be a terminal velocity of course will be higher than compared to the others, then catching off phenomena will be more intensive than higher pressure. So, low pressure sometimes will enhance the coalescence phenomena and growth of the bubble. The bubbles grow in size owing largely to coalescence of course, because of the coalescence 2 bubbles will come to each other and making a bigger one. So, it is this is the called coalescence phenomena. So, by coalescence of course, 2 smaller bubbles may become bigger one. So, from the bottom to top you will see there will be a trend of that coalescence phenomena in such way that at the bottom the more number of bubbles will be coming to each other and colliding and making a coalescence, and due to their higher buoyancy, and they will go up, and then after a certain time at a certain distance you will see there will be a bigger bubble formation at a certain location. So, 3 factors mainly that affect on the bubble growth or bubble coalescence. You can say that one is hydrostatic pressure, another is that catching up of the bubbles or trailing bubbles, and then the colliding of these bubbles parallelly, or you can say horizontally. You can say the effect of hydrostatic pressure in this case merely small, whereas the bubbles grow in size owing largely to coalescence there. Now, there are different models available by which you can estimate what should be the size of the bubbles at a certain height of the fluidized bed. So, Geldert 1972 actually they have observed some phenomena of this bubble formation from its distributor, and they also done the experiment with the group B powders, and in that case that they reported that the fluidization behavior of this group B powders was independent of the mean particle size and the particle size distribution. So, particle size distribution is one of the important factor also there to characterize the fluidization behavior. In particular, it will see that the mean bubble size was found to depend only on the type of the distributor. So, there are various types of distributor that already we have discussed in earlier lectures, that several different type of distributors they have different actually capability to distribute the gas as a dispersed phase of bubbles, and also various distributor will give you the different sizes bubbles. Now, the distance above the distributor plate, of course, that is very important to characterize the bubble size. At the very near to that distributor plate, the bubble size will be very small, whereas above this distributor the size of the bubble will reduced, and there also the frequency of the bubbles will reduced. Frequency means number of bubbles their formation. Now, due to that coalescence, you will see the frequency of course will be reduced because of the coalescence, and this of course formation of the bubbles depends on the gas velocity above the distributor, of course relative to that minimum fluidization velocity. Now, Geldert 1972 they reported that the bubble size depends on this height of this fluidized bed from the distributor plate, and also the relative velocity of the gas or fluid that is maintained inside the bed. Now, this relative velocity is nothing but the what should be the velocity of gas which is used for operation of the fluidized bed, and what will be the minimum bubbling fluidization there. So, u minus u m f there will be the this is called the relative velocity here. So, this as per this equation here that as per this equation here given dB will be equal to dB 0 plus k into h to the power n and u minus u m f to the power m. Here this k, n and m are coefficients that will be obtained from the experimental observation. Now, this dB 0 is called the initial bubble diameter that is being produced from the distributor plate here in the fluidized bed, and k is the constant. Of course, this will characterize that how bubbles are actually moving from this distributor plate to the top of the fluidized bed, and it depends on the path of the bubble. And this n and m, these are coefficients. Of course, this depends on different operating condition as well as the systems of the fluidized bed here. Of course, it depends on the particle diameter of this particle size and particle size distribution that will also effect on this bubble diameter. Now, this m and n will be experimentally obtained by changing this operating variables and also the system properties, and by doing the experiment and calculating the bubble diameter, and they are making these correlations. Of course, this dB 0 it is very difficult to calculate this initial bubble diameter from this distributor, but you can obtain this here if you just feed this dB data in terms of this u minus u m f and h n h, then you will be getting them that from the profile as a intercept, and this what is the coefficient here. From those factors, you will be able to find out what will be the initial bubble diameter. And of course, this initial bubble diameter will be varying according to the flow velocity, and also that depends on the type of distributor there. It is seen for porous plate distributor, and that this dB will be is equal to here 0.915 into u minus UMF to the power 0.4. What does it means? This actually this portion is nothing but the initial bubble diameter. So, this initial bubble diameter denoted by dV 0 is a function of here relative velocity of the gas compared to the minimum fluidization velocity, and also it depends on this factor h, that is at a certain height, and what should be the coefficient for m here, m is equal to 0.94. And if you are changing this n is equal to 1, then of course, you will see there will be a bubble diameter at a height h or n varying, that depends on the physical properties of the system. Now, this correlations of course, here applicable, or this correlations has been made by doing the experiment with the porous plate, where the porous plate will be consisting, or porous plate consists of one hole per 10 centimeter square area of the bed. So, based on this porous plate distributor, you can obtain, you can calculate the bubble diameter at a certain height and at a certain gas velocity, and also the initial bubble diameter of course, you will be having from this correlations at a certain gas velocity there. But for orifice plate distributor, you will see this initial bubble diameter that depends on the number of holes in the porous orifice plate distributor. So, in that case, if number of holes increases, you will see the bubble diameter will be, initial bubble diameter will be less, whereas if you increase the gas velocity and fixing of fixed this orifice plate hole numbers, then of course, there is a possibility of increase of bubble diameter there. So, to get the less diameter bubble, or less size bubble diameter, or you can say the smaller size bubble diameter from the distributor, you have to increase the orifice hole number there, that is denoted by NOR. So, dBO here, the initial bubble diameter for this orifice plate distributor is a again can be calculated from this correlations here. So, 1.43 into u minus UMF by NOR to the power 0.4 here into here g to the power minus 0.2. And then if you substitute this dV 0, that means initial bubble diameter here in this equation, then again you can calculate this dB at a certain height and at a certain gas velocity that is operated that governs the fluidized bed. Then what should be the bubble diameter inside the bed for this orifice plate distributor. So, in this case of course, you can get the smaller bubble size if you use the plate distributor of large number of hole, and of course, if you increase the gas velocity, there will be a possibility of this higher diameter. So, optimum condition will be that you have to design the distributor in such a way that to get the smaller bubble size distribution for the more beneficial mass transfer operation, you have to have a smaller diameter and of course, to get the more interfacial area, so that you can get more mass transfer in this case. So, for getting more mass transfer area and getting more performance of this fluidized bed, this orifice plate distributor with the large number of porous plate will be more suitable compared to the porous plate distributor there. Mori and Wen, if in 1975, they have developed another correlations to calculate or to predict the bubble diameter inside the bubbling fluidized bed. they have observed that from the distributor there will be a chain of bubbles that is forms from this distributor to that to the top of the bubble here. But at the distributor there will be very small bubble, whereas they are going up, they are observing that relatively higher size bubbles are there, and at the top it is almost, you will see there will be a maximum bubble diameter. So, here in this case two bubbles may be colliding vertically and then touching to each other or capturing each that is leading one to that trailing one, then and getting the coalescence and becoming bigger bubbles, and at the top it will be moving there, and then the maximum bubble size will be there. So, in that case Mori and Wen based on this actually happening, they have developed these correlations here whatever shown here, and they have assumed that all the gas above the minimum fluidizing velocity went to form a single train of bubbles rising along the center line of the bed and circulated that can be calculated the diameter of the bubble with the bed height h as per this correlation here. So, what is this here? dBm minus dB divided by dBm minus dB0, that will be equal to exponent of minus 0.3 into h by d bed here. This d bed is the bed diameter, and here dBm is the maximum bubble diameter, and dB0 is the initial bubble diameter. So, you have to know the initial bubble diameter and also what should be the maximum bubble diameter, and once you know this maximum and minimum bubble diameter at a certain height here, suppose here at a certain height here, this is the maximum bubble diameter and this is the diameter at this height is, and this is the maximum bubble diameter. So, what should be the size of this bubble that you can obtain from this equation. Now, you have here only you have to know what is the height here from the distributor, and also what would be the initial bubble diameter, maximum bubble diameter, just substitute here, you will get the maximum value. Also, you have to know the what will be the diameter of the bed. So, except this dB, everything is known to you, this h, d bed, dB0 and dBm, then you will be able to calculate what should be the bubble diameter at this particular height. Now, according to this Mori and Wen 1975 model, the maximum bubble size depends on only this relative velocity of the gas to the minimum fluidization velocity and also the cross sectional area of the bed. So, the dBm, this maximum bubble diameter will be equal to 0.652 into cross sectional area of the bed into this relative velocity of the gas to the minimum fluidization velocity, that is to the power 2 by 5. Now, we have of course earlier that discussed how to obtain this maximum bubble diameter by photographic method. If you use the high speed camera as well as the microscopic camera, there you will observe that what should be the exactly size of this bubble diameter after analyzing it by suitable software of image analysis, then you will be able to calculate what will be the maximum bubble diameter there. So, once you know that maximum bubble diameter with respect to different operating conditions, then if you make with this correlations with the experimental results, you will get this type of coefficient of 0.6522 by 5. Of course, these coefficients may be different from different experimental results, maybe that depends on the system to system also of course. So, you can get the idea to calculate the maximum bubble size from these correlations. Also, from your experimental data you can also make one correlations in this way, so that you can predict your maximum bubble diameter. So, this maybe there the error will be maybe some extent that 10% or 15%, that can be acceptable, but if you try to make the correlations in this way, you will be able to do in your experiment. Now, initial bubble size as per this Mori and Wen model, for perforated plates they measured this initial bubble size and the initial bubble diameter from their experimental data. They have correlated to predict this initial bubble diameter as this, and they told that this initial bubble diameter depends on the number of what is that orifices, and also the bed diameter and the relative velocity of the gas with the minimum fluidization velocity. So, again here you can also make this type of correlations just from your experiment. Otherwise, you can directly use this correlation to calculate the minimum bubble size from the distributor here. So, these correlations, of course, all correlations whatever will be made from the experimental data will be validated within a certain range of operating conditions. So, these correlations is valid here it is seen that this bed diameter will be within the range of 30 to 130 centimeter, and minimum fluidization velocity should be within the range of 0.5 to 20 centimeter per second. Whereas, this particle size of course, it has a of course, immense effect on that initial bubble size. Then these correlations, of course, this validated within the particle size of 0.00 meter to 0.045 centimeters, so 0.006 to 0.045 centimeter. And of course, this relative velocity u minus EMF should be within the less than 48 centimeter per second. So, within these operating conditions you can use these correlations to predict or to calculate the initial bubble diameter for the perforated plate distributor. For porous plate distributor, again they have developed one correlations here. They have seen that this initial bubble diameter directly related to the relative velocity. Now, they have seen that this initial bubble diameter is the proportional to the square of the relative velocity, and this proportional constant is 0.00376. So, these following expressions can also be used to calculate the initial bubble diameter. Now, this again correlation will be validated within a certain range. In that case, this correlations is valid if the bed diameter is within the range of 30 to 130 centimeter, and this minimum fluidization velocity will be within the range of 0.5 to 20 centimeter per second, of course, within the same particle diameter range and operating variables operating parameter like the gas velocity will be within the range of this UMA plus 48 centimeter per second here as per equation. Now, Rao et al. Of course, 1976 he also suggested the following equation to estimate the bubble size in the fluidized bed. They have obtained that this bubble size is a function of this relative velocity as well as height and the gravitational acceleration. Here one important parameter is empirical constant, here H0 is inserted here based on this correlations. Here dB is equal to u minus UMF to the power half into H plus H0 to the power 3 by 5. Here this H0 is the one empirical constant, and it is characterized based on that what is that distributor, and it is seen that this H0, this empirical constant, it will be 0 for a porous plate distributor, and it will be greater than 1 meter for large 2 years types distributor. So, this bubble diameter you can obtain or you can predict or you can calculate only if it is produced from this porous plate and large 2 years, then you can say what should be the bubble diameter at a certain height. Darton et al. 1977 they have also given another mechanism and also that mechanism to grow the bubble and also what should be the frequency of that bubbles, how many bubbles are forming in the fluidized bed. Based on that they have actually suggested different correlations to calculate the bubble size. Now, they have assumed that the bubbles are lined up as close together as possible as per this figure, and they also defined a so called, it is called catchment area, and catchment area for each particular bubble track. This is the particular bubble track here, and the bubble frequency can then be calculated by this bubble rise velocity upon the diameter of the bubble, and diameter of the bubble, and with the bubble velocity here, this bubble velocity will be equal to 0.11 into g d bed to the power half here. So, based on that, the bubble flow in each track they have suggested how to calculate there, and according to their model, then this bubble flow that is u minus UMF, that is called relative flow of the bubble, can be calculated from this two phase theory as per these correlations here. This will be equal to pi dE to cube by 6 into UB by 2 RB here, whereas dE is called equivalent bubble diameter, because here this equivalent bubble diameter is that all bubbles may not be the same in size and also same in shape. So, in that case you have to calculate from the equivalent bubble diameter, and what should be the bubble rise velocity that has been given earlier in this the bubble rise velocity can be calculated by this correlation, and here this RB to RB is the bubble diameter here, and then from this you just directly substitute the bubble rise velocity here, then you can calculate what should be the relative velocity of the flow of bubble inside the bed. And if the bubbles are hemispheres, the bubble of each individual bubble can be calculated by the equation here. So, all bubbles may not be spherical, some bubbles will be what is the hemisphere. So, in that case this hemisphere 2 r b cube by 3 is equal to pi d b cube by 6, this will be satisfied here in this case to calculate the equivalent bubble diameter just by considering that there is a spherical bubble here. And then after substitution, the dB is 0, that means initial bubble diameter, equivalent bubble diameter can be calculated from these correlations here, will become 1.63 into u minus UMF into a cas by root over g to the power 2 by 5. What is a cas is called catchment area. The catchment area, what is that catchment area? Catchment area is defined as the area of distributor plate per hole. That means area of distributor plate per hole. Per hole, what how many area is occupied there, that is catchment area. So, once you know that catchment area and the relative flow of the bubble, then what should be the initial bubble diameter you can calculate from this correlation. And when there are two bubbles of equal volume, they are coming to each other, and from the nth stage they are coming, there is the nth stage they are coming, then how they will be collapsing and how they will be coalescence to each other to form a bubble of size, a particular size in the n plus 1 stage there, then you can say that that will be the here this at this stage this n is equal to n plus 1 stage, this equivalent bubble diameter will be equal to cube root of this 2 into dBE to the power n here. So, from this relationship you will be able to calculate what should be the equivalent bubble diameter at a certain stage. So, if you consider the stage, that initial stage from this distributor n is equal to 1, and then the next stage n is equal to 2, what should be the bubble size, and then nth plus 1 what should be the bubble size here. So, from these different stages how these bubbles will be growing up to the top, based on these stages you will be able to find out from this correlation. So, this will give you that what should be the equivalent bubble diameter at nth stage here according to their model. And if you further assume that the height of each bubble coalescence stage is proportional to the diameter of the catchment area, you can get this what should be the catchment area here. This will be considered as pi by 4 into d c square. That means, here cross sectional area of the column to be considered, and also h there should be considered as at a certain height, that will be some factor multiplied by d c here. This is the column diameter, where this is the diameter of the circular catchment area for each bubble stream, and h n is the height of nth stage. So, at nth stage height, at a certain height, then what should be that this h that should be multiplied by lambda. Now, what is that lambda factor? That lambda factor is nothing but here that lambda factor generally is considered according to their model, and based on their experimental data, they suggested that lambda should be equal to 1.17. That means, h at the h, that is 1.17 times of that catchment diameter or area, then you can obtain what should be that h value, and at that h value, at that certain stage, what should be the actually bubble diameter that can obtain from this relationship here. Now, this here h n at a certain nth stage, what should be the n here? That will be equal to lambda into d c 0. That means, for the initially what should be that bubble diameter, and then what should be the catchment diameter initially, that this will be d c 0, and then what is lambda d c 1, d c 2, lambda d c n minus 1, that catchment area of the bubbles there at the nth stage. Of course, you have to calculate that what should be the h in there based on this value. Now, since this dBn that will be equal to this here as per this at nth stage, what should be the equivalent bubble diameter that can be obtained from these correlations, then what should be the h n value, then you can obtain by this relationship, that will be equal to 0.62 into z to the power 0.25 into lambda divided by u minus u m f to the power 0.5 and dBe, that means equivalent bubble diameter to the power 5 by 4 initially what is that, and summation of that n is equal to 0 to n minus 1, that is in nth stage up to that 2 to the power 5 n by 12. So, here this h n depends on this flow or velocity of this bubble, as well as the diameter, equivalent bubble diameter, and also the number of stages there. So, in that case how to calculate this h n, you can of course will be obtained from this. Now, lambda should be equal to 1.17. Now, with this equation of h n, if you once you calculate this h n, then what should be the bubble diameter at that particular nth stage, you can calculate here by this 0.54 into u minus u m f into h plus, here h should be h n here, or okay, of course, this is very simple, that h n means at a certain height of the bubble fluidized bed, then h n plus 4.0 into root over catchment area to the power 4 by 5 by z to the power 1 by 5. So, from these correlations you can obtain what should be the equivalent bubble diameter. And then what should be the total bed height then, as per that, suppose there is a from the beginning to that at a certain height, the all bubbles will be coalescing to a single bubble. So, based on that, what should be the total height of the bed based on this case, that is the coalescence of these bubbles, the total bed height then can then be expressed as here h will be equal to 1.85 g to the power 0.25 into lambda by this here into dBe nth stage to the power 5 by 4 minus dBe at the initial stage to the power 5 by 4, and then from this what should be the total height of the bed you can calculate here. Now, if the bubbles grow to the size of the vessel diameter, the bed becomes a slugging bed. From this analysis, this occurs at the following conditions. Here you can say h by d bed, if it is greater than 3.5 into 1 minus 1 by root over n var, you can say that there will be a formation of this bubble in such a way that the bubble size will be of almost equals to the vessel diameter, and in that case the bed will behave like a slugging bed. Zenz 1977 they have proposed another model to calculate the bubble diameter here. So, they have assumed that bubble growth in the fluidized bed that resembles the well known, that is Fibonacci series that is given by Zenz 1978, and proposed the following equation for bubble growth here. In this case, this the ratio of the bubble diameter at a certain height to the initial bubble diameter, that will be equal to 0.15 into h by dv 0 plus 0.85. So, this 0.85 is nothing but this intercept here, intercept, that means if you are getting this dv by dp 0 from your experiment at a certain height, then what should be the value? Just a simple, just fitting the experimental data here like this. Here if it is suppose db by here db by db 0 and here h by dv 0, if you have the data from the experiment like this, then you can get this type of straight line, where this intercept will give you 0.85, whereas this slopes will give you the value of 0.15. So, from this experimental data you will be able to find out what is the bubble diameter at a certain height there, whereas this height can be calculated as per that Fibonacci series also, that here this h will be equal to dv 0 into summation of cube root over n, and dv will be equal to then dv 0 into here this summation of cube root over n here. So, in this case of course, this n here you will see that Fibonacci series 1, 2, 3, 5, 8 and 13 they are and respective height that denoted by h 1, h 2 and h 3, then you will be able to total height by summation of this here. So, based on this bubble growth by Fibonacci series, this Zenz 1977 they have developed this correlation to obtain the bubble size here. So, these correlations also can be used to calculate what is the bubble diameter at a certain height. Choi et al. 1998 latest that model for the that is for the bubble size based on the coalition theory, and they have developed this model, and they have stated that the bubble moves upward and the time averaged instantaneous bubbles movement at a point a bed cross section is regular, and the bubble speed V b as a constant here, and hence average bubble rising velocity u b is related as half of the bubble speed, and bubble coalescence was considered to occur on a pair of bubbles at a time. So, based on these assumptions, they have actually made one simplified collision theory based on this analysis, based on this mechanism or assumptions, and they have stated different way to calculate the bubble frequency, and the bubble coalescence frequency as per that is per unit volume, that is denoted by FCV is calculated in this way by this correlations FCB, that will be 0.5658 into pi dv square into v into n square here. This n is nothing but the number of bubbles, how many number of bubbles are forming inside the bed, that can be obtained from the bubble diameter, and as well as the what should be the bubble volume fraction inside the bed. If you know the bubble volume fraction inside the bed, and if you know the bubble volume, that is 1 by 6 into pi dv cube, then just the bubble volume fraction divided by the total volume of the bubble, that is the bubble volume into the bubble volume, then you will get the number of bubbles forms here. If you know the number of bubbles there, of course, what will be the frequency of the coalescence, that means what is the probability, what will be the that is how many times that bubbles can coalescence inside the bed per unit volume of the fluidized bed, that can be obtained from this. So, this frequency depends on the bubble size as well as the how many number of bubbles are formed inside the bed, and so you have to know what should be the bubble speed there. So, here this dB and n are the spherical bubble diameter and the number of bubbles per unit volume that should be calculated, and based on that you will be able to calculate what will be the coalescence frequency per unit volume. Once you know this coalescence frequency, of course, you have to know when the number of bubbles is assumed to increase by 1 at a breakup of bubble, there is a possibility to break up also their bubble, then total splitting frequency per unit volume also to be calculated. So, total splitting frequency per unit volume F s can be calculated from this here. This F s will be equal to F s star into n. Here n will be equal to again that what will be the number of bubbles formed here. So, here splitting frequency per unit volume F s is equal to this F s star is the average splitting frequency of an original single bubble here. This is the original single bubble. If you splitting have the splitting frequency for the single bubble, then you have to multiply by the n number of bubbles, then total you will see that splitting frequency per unit volume inside the bed will be equal to F s star into n. Now, we know that then coalescence frequency and the splitting frequency. So, once you know that coalescence and splitting both will be there, then of course, the effective then what will be the effective manner by which that you can get the effective bubble number, because one maybe that bubble maybe will be splitting as well as coalescence. So, once it is splitting, then two bubbles again make coalescence. So, what will be the effective actually number of bubbles will come. Now, the variation of then number of flow rate NF, number flow rate, that is number flow rate, that means how many numbers are produced per unit time, that means here number flow rate NF of the bubbles across the bed cross section with respect to height h above the distributor is then calculated here in this way. So, this is d n by d h will be representing by that is number flow rate of bubbles, and that depends on what is that depends on cross sectional area of the bed and the bubble speed, and then what is that bubble volume fraction inside the bed, and bubble diameter, and what will be the bubble splitting frequency for single bubble. So, once you know this, then from this correlation you will be able to find out what will be the rate of number of bubbles formations there inside the bed. Now, if you consider that initially as an initial condition that NF will be equal to NF 0 at h is equal to 0, and also if you are considering that bubble rise velocity as UMB is equal to UMF, and the volumetric flux that is QB will be equal to U into U minus beta into UMF, then the number flow rate NF of the bubbles across the bed cross section and bubble void is epsilon b then can be calculated from these equations. Here NF will be equal to 6 into U minus beta UMF into A divided by 5 dB cube, whereas this bubble volume fraction that depends on the velocity of the gas and also what will be the bubble rise velocity there. So, this will be equal to U minus beta into UMF. UMF is the minimum fluidizing velocity, and also UB is the bubble rise velocity. Here in this case beta is one coefficient. This coefficient of course depends on the experimental data, actual condition. In actual condition, what should be the bubble actually flux, volumetric bubble flux inside the bed, that depends on this particle size and size distribution, and also what will be the system used there. So, that depends. So, this beta factor also depends on the operating condition. Now, this U generally it is seen that this beta is equal to 1 in many cases. So, almost equals to 1. So, what will be the bubble rise velocity will be equal to u minus u m f plus 0.11 0.711 into z dv to the power 0.5. And for coarse particles the minimum bubbling velocity equals the u m f, but for the fine particles it is much larger than u m f. So, this beta of course depends on the bubbles particle size also. For coarser particles it will be different than finer particles. And of course, if this bubble rise velocity is equal to V b by 2, the variation of bubble diameter d b with respect to height h will be equals to then d b by d h, that will be equal to how actually the bubble diameter with respect to height will be changing. Then you can calculate from this correlation here. This will be equals to 2.264 into u minus beta of u m f. Then that depends on this also this bubble frequency, splitting frequency, and also bubble rise velocity there, with an initial condition that d b is equal to d b 0 and h is equal to h I. That means here h 0. So, with this initial condition, if you integrate this, you will be having that what should be the bubble diameter with respect to height. Now, Glicksman et al. 1987 considered the mean coalescence rate while assuming the bubbles were in a random spatial distribution like that of the present Choi et al. Model here. Now, if the coalescence frequencies is equal to bubble frequencies, both are same, then the bubble diameter becomes the equilibrium bubble diameter. So, that will be equilibrium bubble diameter, then will be obtained from this the equilibrium of these frequencies and coalescence and breakup frequencies. So, this will be equal to 6.792 into u minus beta into u m f by f s star. The equilibrium bubble diameter increases linearly with the ratio of volumetric bubble flux to the splitting frequency of a bubble. So, this bubble flux q b can be obtained from this u minus beta into u beta times of what is that minimum fluidization velocity, where beta can be calculated here u minus u m f to the power 0.620. So, here this depends on particle size, because that particle size will be the minimum fluidization velocity. So, from that minimum fluidization velocity, what should be the beta factor, that what will be the ratio of this u by u m f, and from which you will be able to calculate this beta here. And substituting this above equation of equilibrium condition and with the initial boundary condition, the variation of bubble diameter d b with respect to height h can then be expressed as by this equation this here. So, from this equation you will be able to calculate what should be the bubble diameter at its equilibrium condition. That means, where bubble coalescence and bubble breakups of its frequency will be same. So, in that case from this relationship you will be able to calculate the bubble diameter at its equilibrium condition. Here some coefficient here a and b are there. So, this a and b value will be obtained from the experimental condition, and then here this a to be calculated here and b to be here in this way, and this b here. So, f dot s star, that will be equal to here from this correlation you can obtain what will be the value for this f s star, and then d b 0 can be calculated if you are using perforated plate distributor, and if you are using porous plate distributor d b 0 can be calculated from this. So, once you know this a, once you know this a, b, and what is that f star and then d b 0, then you can calculate what should be the bubble size at equilibrium condition there. Now, from this graph we can observe that how bubble size is changing with height of fluidized bed and fluid velocity that is shown by the Choi et al. In this case, see here bubble size is increasing, and then it will be coming almost constant here with respect to different gas velocity, and at minimum fluidization velocity as 2.3 millimeter per second for group A particle. Whereas, here in this case for group B particle here it will be reducing at a certain velocity here, because this minimum fluidization velocity will be less than this earlier minimum fluidization velocity there, and also the size of the particles will be different from then. And group D here, of course, the size of the particles will be more higher than this B and A. So, in that case the more minimum fluidization velocity is required. Because of that, you will get the different value of beta, and from which the coalescence and the splitting frequency will be different according to this function of this CUMF. Now, how then dB will be changing here. So, this is the profile from which you can calculate what should be the bubble diameter at a particular operating variables here. Now, if there is a bubble is producing from the multiple entry nozzles, then in that case bubble growth from the multiple entry nozzles depends on different other parameters here, like that, like what should be the orifice separation distance, what should be the average height above the orifice at which coalescence totally completes, and then volume of the bubble void and its associated gas shell, that following coalescence that can be correlated as this. So, here this AC is nothing but for that what will be the bubble growth here, the average height above which that orifice at their coalescence will be complete, that you can calculate from this, where this LS is nothing but the orifice separation distance. Orifice separation distance means here, so what will be the hole, and then what will be the distance between two holes there. So, here the, and of course, this in that case what should be the volume of bubble void there inside the bed, that will be equal to here 31 times of Vp to the power 0.42. Here Vp is the bubble volume here. So, from this from the multiple entry nozzles, so that the complete coalescence at a certain height, that can be calculated from this correlation. And then pattern of bubble growth and solid circulation, that can be obtained from this here phenomena. So, in this case you will see that all the models for the growth of bubbles in a fluidized bed have assumed the same type of ordered progression and independent of solid movement in the beds, whereas Whitehead 1979 pointed out that the pattern of bubble coalescence and solid circulation in large industrial fluidized bed depend on both the bed depth and the operating variable. And also the figure shows that patterns observed in the large fluidized bed of group B particle with industrial type distributor plates. In this case, you will see for the large diameter there will be possibility of that getting the circulation of the fluid velocity, and because of which the coalescence phenomena will be something different. There will be a intercirculation cell formation inside the bed, and because of which that coalescence and the breakup will be distinct. And then for uniform actually flow velocity, that means here for you will see fully developed flow, if there is no circulation inside the bed, then you will see there will be easily obtained the equilibrium stages, and from which you have a certain height, when that equilibrium condition and the coalescence happens, that you can obtain from this correlation. So, this is the pattern how actually this circulation cell inside the bed and how bubbles are getting interacted to each other. So, it depends on the diameter of the bed, of course. If you are having more diameter of the that means larger diameter of the bed, you are having that chance to get the more circulation cell formation inside the bed, and the energy distribution across the cross section will be different, and because of which there will be a splitting phenomena, different splitting phenomena will be there, and the number frequency of the bubbles will be higher there. and of course, if the bed diameter is less, there will be a formation of slug, and because they are of which that slugging phenomena will be there, number of frequency of the bubbles will be less, and so because of that the flow pattern inside the bed that will governs the how the growth of the bubble inside the bed will happen. So, next lecture will be again we will be discussing what should be the bubble growth, coalescence and breakup inside the bed in case of 3-phase system, that means gas, liquid, solid system. In this case, whatever discussed here only for gas solid system, but the next class will be or next lecture what should be the phenomena that will be discussed for gas, liquid, solid system. So, that is for all today. You can get more information from these two references here, Cooney and Levenspiel, Fluidization Engineering, and also Young that is Young Handbook of Fluidization and Fluid Particle Systems. So, thank you.